So in the last video, we took a look at these two different hypotheses that we could form to help explain why we were getting a sample percentage that was over 50%. And remember now, we're going to start to test hypothesis 1. So let's take a look at part D of this question and see how exactly we're going to plan to test hypothesis number 1, to see how it fits. In section 6.2, this is the section where we talked about the distribution of p-hats. We saw that the sample percentage p-hat followed a certain pattern as long as the sample size was large enough. If we assume right now that both candidates are going to have 50% of the vote, that is, if we assume hypothesis number 1, so if we assume hypothesis number 1, then is the sample of voters that was collected here large enough for the possible values of p-hat to begin to follow a predictable pattern? Really all I'm doing here is I'm going back to the ideas that we talked about in 6.2 and I'm trying to see what distribution my p-hat is going to have. Now in order to figure that out, I'm just going to do some checks that we saw in the last section. You may be able to go back to your formula sheet that was for exam 2 to try to take a look at these. But this was one of the different checks that I was going to need to run. The first check that I was going to need to run was to see if 20 times little n would be less than or equal to capital M. Well, in this case, I have 20 times 800 individuals, which comes out to be 16,000. And I want to know if the number of total people that are going to vote in the entire election is greater than 16,000. Well, the problem said this was like a U.S. presidential election or a presidential election. So, this is definitely going to be true. I don't know how many people show up on the day of the election to vote, but I'm pretty darn sure it's more than 16,000 people. Now let's take a look at number 2. Remember that in number 2, we needed to have n times p times 1 minus p to be greater than or equal to 10. This was the thing that was in question. Well, here I can see that automatically my value of n is going to be 800, but what's my value of p? Notice I don't have a value of p at the moment. And this is why it's so important that we have an initial assumption. We have to start assuming that the value of p is something. And so we're going to be, again, keeping in mind that we're testing hypothesis number 1. We want to see how things will work out if hypothesis 1 is actually the one that's correct. So let's see. How well does this problem work if p is 0.5? Well, if p is 0.5, then 1 minus p is also certainly 0.5, and this is easily going to compute out to just be 200, which of course is certainly greater than or equal to 10. So I can definitely see that both of my checks are met, and so I can say p-hat has a normal distribution, and I can even state very specifically that the average of my p-hat values, remember, is just going to be what I believe the value of p to be, and the standard deviation of the p-hats is actually just going to be given by a formula that looked like this. You might recall it was p times 1 minus p all over my sample size. So this is what I ultimately end up with for this p-hat and its properties. It's got a normal distribution with this. Well, now that I understand how the p-hats behave, I can actually go ahead and try to measure the likelihood of getting the given sample that I actually got. That is, I could go back and say, this value, this 53%, 424 people out of 800, how likely is it to get that if we're assuming that candidate X only gets 50% of the vote overall? Okay, well, let's take a look and see how we would do this. There's actually two different ways we can think about doing it, and I'll show both here. So, first I'm going to remember that I have a bunch of different possible p-hats that I could get. Every time I go out and collect a sample of 800 voters, I could get a new number of people that are going to vote for candidate X. It's not always going to come back 424. And I know that those organize themselves into a normal distribution. The most common result here, the average result, is going to be 50%, and of course I have a standard deviation. Now, we want to go ahead and figure out how weird it is to get something like a 53%. Well, notice here, if I get 53%, I can see that it's above average. And so I might want to know, is it weirdly high? Is it weirdly above average? So to determine that, we're going to go ahead and shade above over here because we want to figure out if this value of 0.53 is in the top end of the distribution. Remember, this is how we determined rarity even back in the previous sections. So I want to go ahead and measure what is the chances that p hat is going to be greater than my 0.53. And if I go ahead and measure this, since I have a normal distribution, I can go ahead and use a normal CDF. I can start at 0.53. I can go up to 1E99. My mean is 0.50. And my standard deviation is my 0.5 times another 0.5 over 800. Now I'm going to leave it to you to go ahead and double check me on my calculation here, but I believe I get back a value of 0.0448. And since that value there is falling underneath the value of 5%, we would say that this value of p hat is rare to see if the real value of p is 50%. So again, we're trying on this first hypothesis, and we're saying, it'd be pretty surprising to see what we saw if the first hypothesis is correct. It would be weird to see what we saw if the first hypothesis is correct. Now, another way that we could go ahead and attempt to measure this is using a z-score. So I'll write down here that we could also use a z-score. So to go ahead and calculate this z-score, remember we're going to be trying to find a z-score for our green value here. So to compute that, I would just have to say I had the value of 0.53, I'd have to subtract the value of the average, and then I would have to divide by the corresponding standard deviation, which is this really, really nasty looking value here. Now, I oftentimes don't try to type all of this into the calculator directly. I'll usually try to do something like 0.03, which is what I would get when I subtract the top, and then divide by my entire square root. It helps to just avoid any sort of calculation error that you might accidentally make with order of operations. If you do want to type this into the calculator all at once, make sure that you do put parentheses around what we have up top. Now, if you go ahead and crunch this out yourself, you should be able to see that you get roughly the following value back. You get 1.6971 if you round it off to 4 places. Now, you may recall from at the very beginning of the semester, we said that if I ever got a z-score that was above 1.5, then that would mean that my value that I found the z-score for would be a little bit kind of entering into the rare zone. If you get over 1.5 standard deviations away, a value starts to become somewhat rare. So notice what I can do here is underneath these p hat values, I can list out my z-score values. And underneath my green value, I can list my z-score of 1.6971. So this value is about 1.6971 standard deviations above average. I can also state that here, clearly 0.50 is 0 standard deviations above average because it is the average. So both of these numbers, the probability and the z-score, are going to help me answer part F. Which hypothesis may seem like a better explanation? Well, again, if we're trying on hypothesis 1, we're saying, let's pretend that the percentage is 50%. Then, how weird would it be to get our sample? And our answer is, well, it seems like that's not a very likely probability. It's kind of weird to get that sample. Hey, it's, I see from the z-score, that's kind of entering the rare zone. It's over 1.5 standard deviations away, so it's kind of rare. So we're trying on that first hypothesis, and it doesn't seem to be fitting well. So we would go ahead and reach the following conclusion. We could say, because of our result, from part E, we should say that hypothesis 2 is the better explanation for why we got our p hat value. Because again, just recapping one more time, if I say that the real percentage for p is this 0.50, then the chances of getting this by just dumb luck is actually pretty rare. It's hard to be that lucky. This doesn't seem like the best explanation. So we try on this first hypothesis, it doesn't fit well, and so we ditch it and we go with hypothesis number 2. So now let's go ahead and take a look at the very last question that's on here. Ultimately, this is the question that we started with. What conclusion then would you draw about the news organization's claim? Well, remember that the news organization claimed that claimed that candidate X would be the person who received over 50% of the vote. And based on what we've seen that hypothesis 2 seems maybe like the better explanation. And notice, hypothesis 2 does say that candidate X would win a majority of the votes. They would get over 50%. So it seems here like the news organization can make their claim reasonably. Okay, so this hopefully gives you an idea of how exactly one of these kind of large-scale hypothesis testing questions actually goes. It's kind of always going to be broken down to kind of these basic parts. Now what we're going to do in the next several videos and examples is to kind of build some more terminology around what's being done here. We're going to try to give some names to these different hypotheses, to the way that we kind of organize our information. We're going to kind of organize our information down here from part E and kind of formalize a way that we can tend to write a conclusion based on what we find in our actual test. And we'll cover again all of that in the videos to come.